Oh, yeah. Before we get started, so this is the email that I got for the video. Person handling it will be with you in 2 weeks. And also, it's like Gracie found this link over here, choosing sex of babies. Gender choice kit for $50. So this is interesting. Yeah. It's what?
Did it two girls and she wanted a boy? And so they put the in a petri dish and do research.
Oh, yeah. So that's different from something like this. So they're actually that guaranteed to be a boy. She had a boy. Yeah. So they have to. I guess they have to make sure because the Y chromosome comes from the father, right? And so they have to make sure that they pick that Y chromosome from the sperm cell so that they can fertilize the egg. But yeah, this is just supposed to be a kit of diet and whatever else that they have. Anyways, that's kind of interesting. All right, back to our presentation here. We're looking at a p-value. So what's going to happen here with a p-value is that it's going to make things a lot easier for us in terms of the calculations, and we are going to rely on technology, computers and calculators help us find p-values. We do run into an issue with the standard deviation. You know how we got like those intervals for the proportion and the mean kind of easily with the calculators. The calculators also don't have the hypothesis testing results for the standard deviation, unless you go see Frank and you get that special program. Then you're all set. So we may explore that in this class. I don't know. I really do want you guys to go see Frank, and he'll give you that sheet, and he'll download all these programs onto your calculator, and you get to do a lot of things shortcut way. But for us, the p-value is going to be important. The p-value here is defined to be the probability of getting the value of the test statistic at least as extreme as the one representing the sample data. So what this does is it more or less ignores the critical value. And I'm going to draw a graph here. Just as an example. What your p-value does is, or the way you define your p-value actually, is to get your test statistic wherever that may be, and then it basically has you compute the region of your test statistic. And this area here is a p-value. But even this has some restrictions, because if it's a one-tail test, then it's kind of as easy as that. If it's a two-tail test, and there's some other complications because it has to be split up into two tails. So the way they tell you to find the p-values in the book is a little bit trickier. than the way we're going to find the p-values. But I think I do want you to figure out how they do it in the book, just to be able to do some of the homework problems. And we can take shortcuts with the inverse norm business. But anyways, the p-value is what we're going to be looking at. And the difference between the first way we did it using the test statistic versus this way of doing it using the p-value is really in the decision-making process. And what I'm going to do is I'm going to go back to our table where I have the 8 steps, and I'm just going to copy the 8 steps again and then change a couple of things within those 8 steps that would have us use our p-value instead of our test statistic. So we'll do that in a minute. But here, let's talk about the conclusions for the hypothesis test. We talked about this already. You only have one of two things. You either reject the null hypothesis or you fail to reject the null hypothesis. No accepting, no alternative hypothesis. And the decision criteria from what we did was we looked at the test statistic to see if it was in the critical region. If the test statistic was in the critical region, we rejected the null hypothesis. If the test statistic was not in the critical region, we failed to reject the null hypothesis. So the other part of that is that what if we're not using the test statistic, what if we're using the p-value? So here's the decision criteria for the p-value. And I got to tell you, this is a lot easier to look at the p-values than it is to look at the test statistic. So the p-value is really a comparison with alpha. So here's the story. If the p-value is less than or equal to alpha, then you reject the null hypothesis. Our p-value is really small, then you're going to reject the null hypothesis. If our p-value is big, now p is a probability value. It's a probability, so it has to be between 0 and 1. So when I say big, that's relative, right? Big means bigger than 0.05 or whatever alpha is. So if the p-value is bigger than your significance level alpha, then you fail to reject the null hypothesis. So really, in that 8-step process, there's 2 steps that I'm going to change and tinker with to make it p-value compatible. So let me do that right now. And in the process, we'll talk about how to find your p-value. Oops. So, using the p-value method, your first 3 steps will still be the same. Your next 3 steps will be almost the same, except step 6, instead of using the critical values and using the table and then drawing the tails and all that stuff, you're going to be finding your p-value. And your decision criteria will be a comparison with your p-value. So if PV, let's call a p-value PV, is, what is it, bigger than or equal to? Less than or equal to? Alpha. then we reject the null hypothesis if the p-value is strictly greater than alpha, then we fail to reject the null hypothesis. So steps 6, if we want to be kind of watching out for this difference, step 6 will just have you focus on finding the p-value instead of finding the test statistic. Step 7 is now just going to be a comparison between the p-value and your significance level, which we were supposed to be identifying in the 4th step. And so I think a comparison between two numbers versus critical values, test statistic, drawing, finding the tails, all that stuff, I think the p-value method is going to be a little bit easier for us. So how would you find the p-value? So I'd like to insert the p-value method in here. And the way we're going to do this is we're going to use our calculator. We're still going to have to gather statistics like we did before. We're still going to need to use the statistics that we had before. But in our calculator, you know how we had those intervals? Well, the counterparts are the tests. So let's go to stat, tests, and for the first one, for this example, we're going to do, it's a proportion. It uses the z, and then we're going to use a test. Let me start over again. Let me start over again. Because I want to take a picture of it. Sorry. All right. So we're going to pick the one prop z test. And then the p sub 0 is defined to be the p that they have. So in our case, it's going to be 0.5. And then the x and the n are the x and the n from the problem, which was what? 97 for the x and then 100 for the n. Now this last bit over here is the relationship that you have that contains the not equal to, the strictly less than, and the strictly greater than. So what should we be looking at on our papers when we're at this point in our calculator? Well, we're going to be looking at not equal to, but where did you find the not equal to? The what? The alternative hypothesis. So this symbol that you're going to be looking at here, one of three, is going to be the symbol that comes from the alternative hypothesis. Let's put that in our notes. So, what did we say? We said this is your P. Why is this too thick? This is too thick. That's your P. This is your X and your N, clearly stated. And this is a symbol in the alternative hypothesis. All right, did you guys press enter yet? Or calculate? Oh man, I pressed clear. What did you guys get when you hit calculate? 0? So let's interpret our results. What did we get for our results? Now look at this number over here. Does this look familiar? That's your z-score, right? Did we find that before? What's that number? What would you call that number? Yes. You would call this number the test statistic. You know that calculation that we did, or that you guys did, that may have been easy or difficult? In any case, we found it right here. Pretty cool, huh? This one, it says P, which kind of contradicts with our notation because we use a different P, and the P that we use, the calculator calls it P naught. So I'll stop confusing you there. This P, where it says P in your calculator, you should write it on your paper as PV. PV is in p-value. And the p-value is so small here, it's 5.5 times 10 to the negative 21st power, which is 20 zeros before you hit that 5. And when it's really small like this, do we say it's equal to 0? Probability of 0 is an impossible event. Impossible. So this is not impossible. It's unlikely, but it's not impossible. So I would label it as 0 plus, or I would label it with 0.00, or I would label it, or I would write it as 5.5 e to the negative 21. I'll accept that, although not very many people would understand that. If you were to use scientific notation properly, you would say times 10 to the negative 21. So something so small with this many zeros, I can accept a 0 with a plus on it I can accept any of these notations as long as I put this under step 5. This is supposed to be step 6, wasn't it? I'll just change it to a 6. Sorry. Step 6. Okay? Is that good? So now, based on your p-value, so if we were to continue using the p-value method, we say since PV, what's PV? It's almost 0, right? So it's less than alpha. What is it? 5.5 e to the negative 21 is less than your alpha, which is 0.05. So since our p-value is less than alpha, we have the same conclusion. We reject a null hypothesis. And because we have the same conclusion, our step 8 will then be the same. Okay? So what I tried to do there is I tried to, without redoing everything over from scratch, I just tried to look at where the places it would be different from the traditional method, using the test statistic and the graph and stuff like that, versus the p-value method, where you just look at the p-value, the calculator, the p-value, and then compare it with the significance level. Based on that, we only have to change a couple of steps, step 6 and step 7. Everything else remains the same. Okay? All right, let's do some problems from the homework. So I'm going to leave it up to you to try to tackle some of those. Oh, wait, I still have to do error. And then we'll do some problems from the homework. So this is the decision criteria for the p-value. A lot easier, I think, than having to draw the graph and identify the regions and the tails and all that stuff, because our technology will take care of us. So this is something I definitely don't want you to mess with, this whole idea of the p-value using the thing. I know the book or the homework is going to point you towards this if you're working on the homework, but you can use, I encourage you to think about using the inverse norm function in your calculators. No. Maybe. This is the conclusion again, kind of written a little bit differently. And here they give a little statement on why we don't use the word accept. You know, we said reject, right? And then we say fail to reject, but we're not really accepting. What we're trying to do is, our whole purpose, our whole main goal, or the main goal of a hypothesis test is to reject a null hypothesis. If you rejected it, then the hypothesis test did its job. If you didn't reject it, then there's no way of saying that we should accept it. So this is just a good statement to try to remember what the whole idea behind a hypothesis test is and how we don't use the word accept. All right, errors. So imagine the whole thing about this is that we don't know what the actual truth is. What the actual truth with the data is, with the population. So the best we can do is we can conclude that our statistics support our claim, or our statistics rejected our claim, but in supporting or rejecting or not rejecting or whatever it is that we come up with our conclusion, there's still a chance that we're wrong. So a type 1 error would be if you rejected the null hypothesis, but it was actually true. So in our case, we rejected our null hypothesis, right? Our null hypothesis was that the proportion was equal to 0.5. And we went through the process and we rejected it. And so we made our conclusion. So what if we did all that, but in reality, it was true? Then we made some sort of error. And that error comes built into this hypothesis test. So because there's always uncertainty in things, we just have to accept the fact that there are going to be some errors. And a type 1 error is an error of rejecting the null hypothesis when it was actually true. So what's our chance of that error? Our chance of that error is alpha, whatever alpha is. So alpha is usually 0.05. So we can say that there's a 5% chance that we're making this error. We made a conclusion, we stated our conclusion, and we would have to say there's a 5% chance that we're wrong. So that is a type 1 error. A type 2 error is that when we don't reject the null hypothesis, but it was actually false. Now this error can be quantified using another Greek letter here, beta. The actual quantity of beta is more complicated than what we care to see, so we're not going to try to figure out what that beta is. I think it's just important to be able to tell what your type 1 error is and what your type 2 error is. Okay? All right. They have this chart in the book. This is a neat little chart, and what I try to do is I try to look at this as if we were trying to convict somebody who did a crime. So let's think of I kind of was thinking about that recent crime that was happening, but I don't know if I want to spark any strong feelings for or against that crime. Did you guys hear about that teenager who got killed because he had a fake rifle and then a cop? Or we can look at Oscar Grant or somebody. Let's not use any of that. Let's just say, okay, there's this guy who committed a crime. Maybe he committed the crime. I don't know. So this true state of nature tells you whether he actually committed the crime or not. So he committed the crime. realistically. Or he did not commit the crime. He was falsely accused. So he goes through trial. And then in the trial, he was found innocent, or he was found guilty. So if he did not commit the crime and he was found innocent, that's good. That was the correct decision. If he did commit the crime, but he was found innocent, then there was an error in the courts. That would be a type 1 error. It could happen, right? If he actually committed the crime and he was found guilty, then the court made the right decision. If he did not commit the crime and he was found guilty, then that's another error that the court has made. So that's a type 2 error. So you can think about the type 1 and type 2 errors in this scenario, where there's a reality of things that we may never know, and then there's a decision made by something. In our case, the decision was made by the statistics through the hypothesis test. Or in this example that this analogy that I'm trying to make, the decision was made by the courts. The court made this decision based on a process. Now that process, as sound as it might be, still has a chance for errors. And so that's the same thing with statistics. So the error could be the court found him innocent, but he actually committed the crime. That's too bad. But that's an error that people take a chance. Or he did not commit the crime, but he was found guilty. That's another type of error. So those errors happen in that scenario. The same sort of errors can happen with our hypothesis test. Pardon me? Well, the kinds of things that cause errors would be the collection of the sample. If we took a sample and it wasn't a very good representative sample, then that could be the error that we would have found. That's the only one I can think of right now. Okay? So in an actual trial, right, error could be found in the jury or in the presentation of the facts by the lawyers and stuff like that. So there's a lot more room for error in that scenario. Here, we have a step-by-step process that have been kind of tested as sound, and so those errors could still happen. Yeah, that could also, again, it's a choice of the sample, so that sample can bring you those errors. But aside from the sample, everything else, the process of this thing is pretty sound. Okay, I think we won't talk about controlling the errors and the power of that. This is a step-by-step process that you would see in the book. At the end of section 8.2, you have two of these. One of them is called the p-value method. The other one is called the traditional method. And so we basically covered those two things in our chart that we created. All right, we don't need to worry about the rest of this stuff. So I think now would be a good time to the examples that they have here for each of the sections cover a set of requirements and then they cover a process of doing it. So what I'd like to do now to begin each section, and with the hopes of trying to get through all the sections before we leave, is I'm just going to cover the requirements, and then we'll do a quick example from the text, from the homework. Okay, so I'm actually going to pick a homework problem and then do it, and then check our answers. And I'm going to do it using the p-value method. Well, I'll do it according to what they're asking for, but I'm going to focus more on the p-value method, or at least the calculator way of doing it. All right. So section A3 is basically the example that we had already done, and it's testing the claim about a proportion. So the important part about this section, aside from what we've done already, is the requirements. So here are the requirements, and again, with the confidence intervals, this looks very similar, right? We're talking about a simple random sample and binomial distribution, and then n times p is bigger than 5, n times q is bigger than 5. These are, if not exactly the same, it's very close to being the same as the requirements for estimating a proportion back in Chapter 7. So I'll say compare with Section 7-2, the requirements that you find in Section 7-2, since they are talking about estimating proportions, should be almost exactly the same, if not exactly. So they do have this thing about the mu and the sigma, and they bring that up to say we're going to use the z distribution, the standard normal distribution, to approximate the binomial distribution. We skipped over that section, but it's not going to be that important for us. Okay. So there's some notation here that we've already talked about in the test statistic that we saw, and the p-value method is going to be just taken from the taken from the calculator. So I think I have one problem already pulled up over here. It's kind of small, but I hope you can still read it. Can you read it? We have 3,009 adults were surveyed, poll. 76% said that they use the internet. Is it okay for a newspaper reporter to write, 3/4 of all adults use the internet? Why or why not? They want us to identify the null and alternative hypothesis, p-value, conclusion about the null hypothesis, final conclusion that address the original claim. Use a p-value method. So let's approach this using the 8-step process that we've already discussed and see if we can do all that identification business. So step 1, what is the claim? The claim, in this case, is what? 3/4 of the adults use the internet, right? So it's kind of important to state your claim first in words, so that you can use those very same words at the end when you start to say things in non-technical terms. And then, from here, try to figure out what the mathematical equivalent of that is. So this is a proportion, Maybe I should have asked you that. Is it a proportion? Yes. So it's a proportion, and we want this to be some symbol comparing a number. So what's a symbol and what's a number? So equals 0.75. You can use a fraction too if you want. You can use 3/4. So this is our claim. Is that cool? So the opposite is what? Not equal to. Oh, this is going to be the same as the problem we just did. I was hoping we'd do one with the greater than symbol, but let's work with this. Should we work with this, or should I find one that has a greater than symbol? What? New one? Okay. Scratch this. Let me just check. Should be A, right? Fantastic. This one. This one will work. This one has more words. Sorry if you're trying to copy this. Oh, this time it was 61,646 people. It's a lot more. Included several questions about office relationships. Of the respondents, 26.6 reported that their bosses scream at employees. Use a .01 significance level to test a claim that more than 1/4 of the people say that their bosses scream at their employees. How is the conclusion? Blah, blah, blah. Let's just worry about those first few sentences to get started. Okay. In words, what is my claim? So literally just get it from reading. Read it, and then they usually have the word claim or test something. Sometimes they don't have the word claim, but you can just tease it out of the sentences that you're reading from the paragraph. Remember, Frank said, this is all word problems, but they're all structured so that you can find key words that would trigger something in your head and say, oh, this is a proportion. Oh, this is the claim, and things like that. So this is a proportion since we're at this section. P. So what's my claim in mathematical terms? P is what? Greater than. Strictly or greater than or equal to? Strictly greater than. 1/4. You can use 1/4 or you can use a decimal equivalent. So the opposite. So this is where the less than or equal to comes in. So if your original claim didn't have a condition of equality, then your opposite has to have a condition of equality. Oops. So it's less than or equal to, right? So from here, you can identify your null hypothesis and your alternative hypothesis. So H naught. Which one is H naught, the claim or the opposite? The opposite is the one that has a condition of equality. And then the original claim, in this case, happens to be the alternative hypothesis. And just for good measure, I usually, when I write down the null and alternative hypothesis, I put a little parenthesis next to the claim, whichever one the claim is. I would normally be writing this in a vertical manner. I got number 8. What? The order is not different, but the numbers might be different. So, all right. What's step 4? So the significance level is alpha. And what is the significance level in this case? So if it's not given to us, we're going to assume it's 0.05. But if it is given to us, make sure you use the one that they give you. Okay? I should do some highlighting here. I guess that's not going to work. Let's try this one. So significance level, your claim. And then we'll highlight some of the other values that we need. So in step 5, we need to identify some important values. So we're using the test statistic that has p's, p hats, and n's and stuff like that, and x. So let's take a look at our problem again and see if we can identify the important things. What if you're going to use a calculator? Do you remember what they look for in the calculator? X and n and p. So we know that p is equal to 0.25. So we need to figure out what x is equal to and what n is equal to. N is usually going to be flat out given to you. X may or may not be given to you. Let me tell you now, X is not given to you here explicitly. So what is N? So N is 61,646. We see another value here, 26.6%. That is not X. What is that? Percentage of N, which is, what do we look at that? We look at that as something. We look at that as what? This is a proportion for the sample. What is that? What is the symbol? How can I ask my question? Yes, thank you. I'm going to ask my question so you guys will tell me what the correct answer is. This is p hat. Well, I was just trying to see. I wanted you guys to tell me what 26.6% was. 26.6% is not X, but it is p hat, right? It's the proportion that you get from the sample. So if you know what p hat is, and you know what X is, no. Let me start that over again. If you know what p hat is, and you know what n is, you should be able to find x, right? So x is equal to, if you remember, it's equal to p hat divided by n, right? With a little algebra, p hat is equal to x over n. So with a little algebra, you can figure out what x is equal to, right? X is equal to what? X then is going to equal to p hat times n. So let's take our calculators out and put p hat times n and tell me what it is. What?
13932.
Wait, so because it's a percentage, you have to divide first by 100?
Yeah. Or you can multiply by 0.266. Okay, let's try to say it again.
60,336.
Okay, so this is x. But remember that x is a whole number, needs to be a whole number. So we're gonna want to round this off to 98. Okay. So I think that's all the information you need, and then from here you can use your calculator. Do one prop z test. So let's take our calculators out and take a look at that one prop z test business. Can't get it any smaller. All right, so stat, test, one prop z test. What's our P naught? Remember, P naught is whatever the claim was, right? Or the null or alternative hypothesis, that number. So 0.25. Now x, now if you didn't calculate x right here and there, right, before we started this step, you could have still gone, what is 26.6%? So that's 0.266 times 61646. So what's cool about this calculator is you can actually do the calculation here and press enter, but you have to go back there and remember to round it off. So I'm going to round it off. That's the same number that you guys got, so I'll just round it off to 16,398. And then we got a 61,646 for our n. Okay, I have three options here. Which one do I choose? Look at the alternative hypothesis, right? The alternative hypothesis is a greater than sign. So just press calculate, and you should be on your way. So not only do you get the p-value, but you also get the z-score, the test statistic, and that's always good to have. So again, we identify our test statistic, and then our p-value. Remember that I want you to write as PV. And with something like this, it's small. So in our decision step, since PV is what compared to alpha? Is what? It's less than, right? This is very close to 0. Alpha is 0.01, but this is less than 0.01. So since alpha is, since the p-value is less than alpha, what do we do? We reject the null hypothesis. So, based on our what? Based on our table? Do we does the original claim contain the condition of equality? No, right? Did we reject the null hypothesis? So our conclusion says the sample data support the claim that blah, blah, blah.
Is that flowchart the same as the other one?
It's the same thing, except they kind of did it diagonally instead of straight horizontal and vertical lines. So we make a conclusion. The sample data support the claim that, what was the claim again? More than 1/2 of the people. And just copy exactly word for word what the claim originally was, and then that's all good. Non-technical terms, and you're using the same wording as what was in the problem. Okay? Let's see if we can get a bunch of fantastic, good job, excellent things here. Identify the null and alternative hypothesis. Okay, so already there's a little bit of a discrepancy versus the things that I'm telling you, versus what's up here. Our null and alternative hypothesis, according to what we have, is the null hypothesis is less than or equal to, and then the alternative hypothesis is strictly greater than. That's different from the choices that they have here, it looks like. It looks like their null hypothesis is exactly the same for all of them. Is that okay? Yeah, it's okay. What? Yeah, so what happens is that when they say it contains a condition of equality, they just use an equal sign instead of a less than, greater than. So what's going to distinguish our answer is the alternative hypothesis being greater than. So we look for the alternative hypothesis. That's P is greater than 0.25. Which one is it? F. All right. Let's check the answer. Nice work. what's our test statistic? So our calculator was able to find that for us. 9.18, 2 decimal places, 9.18. Nice work. What is the p-value? Round off to 4 decimal places as needed. It's like 19 zeros, right? So this is probably the best way to describe this, which shouldn't be exactly 0. I guess they take 0. I don't take 0 if it's not 0. I save 0 for impossible events. So I would have put 0.0 or 0 plus if I were writing it on paper. So apparently this does take it. So our conclusion, we rejected the null hypothesis. There is sufficient evidence to support the claim that if the sample is voluntary response, then is the conclusion valid or not valid? Why not? Because it's not a good sample. So a sample that's voluntary response means only the people who want to say something about their bosses are the ones that are, if they're afraid to say anything about their bosses, they're not going to volunteer that information. So I would probably say that this is not valid. Okay? Is that cool?
Wait, so why is it not, might not be valid?
Oh, because it's voluntary.
Oh, that,
Voluntary responses will yield a not good sample.
what if it's say it's like a survey and everyone asks?
Uh-huh.
Okay.
Then that would be okay.
Oh, but it would be valid?
If a survey that everybody was forced to do, or the sample that you selected was forced to, then it might be valid.
Okay.
Let's put this in there.
You have to satisfy the requirements.
Yeah, we didn't check that because they didn't ask us to check it, but normally we should check to make sure that the requirements are satisfied. So we can make a note in our notes about this business about might not be valid because the sample is not good. Because it's a voluntary sample, the sample is not going to be simple and random. Yeah, it's a little tricky.